So let's derive my composite function. So this is my composite function, and it's made up of f1 and f2. f1 being the outside function and f2 being the inside function. f1 of x equals x squared plus 2 over x plus 1, and f2 of x equals 0.5x. So to derive this, we use the quotient rule, and the quotient rule states if h of x equals f of x over g of x, then h derivative of x equals the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the derivative squared. The denominator squared. So f prime of x would equal the denominator 5x plus 1 and the derivative of the numerator, and know that the numerator could also be written as 0.25x to the power of 2 plus 2, because we can expand this. So 5x squared plus 2 minus the numerator and the derivative of the denominator. And all of this over the denominator squared. So now I'm going to keep this as it is. So the numerator derived would equal this times the derivative of this would be 2 times x, and then 2 is a constant, therefore it's 0, minus, we're going to keep the numerator as it is, 5x squared plus 2, and the the denominator derived would be 0.5, and this is a constant, therefore it's 0, the derivative of it. I'm going to keep the denominator as it is. So now, let's simplify the inside of this bracket, and let's multiply this, and let's get 0.5x minus 0.5 times this term gives you 0.125x to the power of 2. 0.5 times 1 gives you 1. Now, let's multiply this and this bracket, and let's multiply the negative by this bracket. So now, 0.5x times 0.5x gives you 0.25x squared, and 0.5x times 1 gives you 0.5x minus, multiplying this gives you 0.125x squared, and then 1 times negative is negative 1. So now we have 0.25x squared minus 0.125x squared. So that simplifies to 0.125x squared. And then now, let's turn these decimals into fractions. And then now we can simplify the denominator into this. X plus 2 over 2 to the power of 2. Let's turn the numerator into and the denominator into this. And then now this divided by this means this multiplied by the reciprocal of this. So that leaves us with x squared plus 4x minus 8 over 8 times now this gives us 2 to the power of 2 times x squared plus 4x minus 8 times 8 can also be written as 2 to the power of 3 x plus 2 to the power of 2. This cancels out. Now we're left with x squared plus 4x minus 8. Let's take this bracket out, it's not necessary, over 2 times 2 to the power of 2. And this equals f derivative of x. F of x derivative. So now, let's move on to finding the derivative of my compound function. So, my compound function is c of x equals c1 of x plus c2 of x. c1 of x equals 0.5 to the power of x minus 1. And c2 of x equals sine x plus 2, which gives us this when you add it together. So now, let's take the derivative of the exponent term. So, the exponent term derived equals 0.5 to the power of x times ln 0.5. And then now, let's derive minus 1. So, that gives us 0. And sine x derived gives us cos x. And then 2 derived is 0. So this equals c of x derivative. So let's analyze the continuity of the piecewise function. So the function is continuous if the limits exist and the point at which the two functions join exists, and the point is equal to the limits. Let's start by finding the limit of c of x as x reaches 0 from the positive side. So the limit of c of x as x reaches 0 from the positive side equals let's substitute 0 to x. So this gives us 0.5 to the power of 0, which is 1, and then that minus 1 is 0, and then plus, and then plus sine 0 is 0, plus 2 is 2. Now let's move on to finding the limit of f of x as x reaches 0 from the negative side. So let's substitute 0 where x is. So 0.5 times 0 to the power of 2 is 0. And that plus 2 is 2. 0.5 times 0 is 0 plus 1 is 1. 2 divided by 1 is 2. Good news, these equal. So now let's find c of 0. Zero 0.5 to the power of 0 is 1, and 1 minus 1 is 0, and that plus sine 0, which is 0, plus 2 is 2. The reason why we use c of 0 and not f of 0 for this is because the restrictions. Now, restrict the domain of f of x, so x is smaller than 0, and restrict the domain of c of x, so x is equal to 0 or bigger than 0. This way we avoid overlap and discontinuity. The function is continuous over its domain, as there won't be any holes or asymptote. The only asymptote that occurs is on f of x, and it is not within the domain of the piecewise function. The intersection of the two functions lies on the same point, and the limit exists. Therefore, it is continuous. Now, let's find the differentiability. So, the function is differentiable everywhere as long as it's continuous and there are no cusps or vertical tangents. So, to find this, let's take the derivative of c of x, which equals ln 0.5 times 0.5 to the power of x plus cos x. Now, let's take the limit of c prime x as x reaches 0 from the positive side. So substitute 0 to x. So now we have ln 0.5 cos 0 gives us 1, and 0.5 to the power of 0 gives us 1. So this times 1 plus 1. So limit of ln times 0.5 plus 1 as x reaches 0 from the positive side. This equals to 0.307. Now, let's move on to finding limit of f prime of x as x reaches 0 from the negative side. So now let's substitute 0 to where x is, and this gives us this. So 0 to the power of 2 is 0, and 4 times 0 is 0, minus 8 leaves us with minus 8 on the denominator, and 0 plus 2 is 2, 2 to the power of 2 is 4, 4 times 2 is 8. This gives us minus 1. So as you can see, the limits don't equal. So the limit of c prime of x as x reaches 0 from the positive side does not equal limit of f prime of x as x reaches 0 from the negative side. Therefore, the limit does not exist. Let's move on to part C. So now we're dealing with the composite function. So let's find the x-intercept of the composite function. So wherever f of x equals 0, that is where the x-intercept is. So f of x is this. And this equals to 0. So 2.5 x squared plus 2 equals 0. We multiply both sides by the denominator, and that gives us this. Sorry about that. And this can be simplified into 0.25 x squared plus 2 equals 0. Now, let's subtract 2 from both sides and divide both sides by 0.25. And then that gives us x squared equals minus 2 divided by 0.25. Now, to isolate for x, we have to get the square root of both sides. So x squared, the square root of x squared is x, and you have this side of square root of this side. So now we're left with x equals the square root of minus 8, as minus 2 divided by 0.25 gives you 8. So this is a negative number, and we can't find the square root of a negative number. Therefore, there are no x-intercept. Now, let's find the y-intercept. So, to find the y-intercept, we have to take f of 0. Because at a y-intercept, x equals 0. So, let's substitute 0 to x. So this again is 0, and that leaves us with 2 in the numerator, and this is 0 plus 1 is 1, gives you 2. So the y-intercept is 2. So let's find the asymptote. So the function f of x has an order higher in the numerator than in the denominator. Therefore, there is a vertical asymptote. So the x value in the denominator that makes the denominator 0 is an asymptote. So (0.5 x squared plus 2 (0.5 x plus 1). This is f of x, the composite function. And let's take the denominator, 0.5x plus 1. Whatever the x value that makes this equal to 0 is where our asymptote is, that x value. So to isolate for x, let's subtract 1 from both sides and divide both sides by 0.5. That gives us 0.5. Minus 1 divided by 0.5 gives you minus 2. And we have an x-intercept at x equals minus 2. Now, let's move on to finding the minimum and maximum points. So, to find that extreme point, we need to find when f derivative of x equals 0. The reason is, when there's an extreme point, the slope of the tangent equals 0, which means the value of the derivative equals 0. Therefore, we find when f of x equals 0. So we multiply both sides by the denominator, which gives us x to the power of 2 plus 4x minus 8 equals 0. So now let's plug this in the quadratic formula to find the x-intercepts of, or the places where x equals 0. So x equals minus 4 plus or minus 4 squared minus 4 times 1 times minus 8, and all of this over 2 times 1. So this gives us two answers. So the first one is x equals minus 4 positive the simplification of inside this, it is 40a, and all of this over 2. And the second one is x equals negative 4 minus 40a all over 2. So this simplified gives us x equals 5.46. And this simplified gives us x equals 1.46. Now let's keep in mind that there's a vertical asymptote at x equals minus 2. So these are extreme points. We don't know if they're maximums or minimums. So let's find if there are maximums or minimums. So we're going to do that using an interval table. So let's find in which intervals f of x is increasing and decreasing. So, and all while we could find if these are maximums or minimums. I'll show you how. So we have minus 5.46 here, and then we have negative 2, and we have 1.46. These are special points. These are extreme points, and this is the vertical asymptote. So this interval is x is bigger than minus 5.46. X is bigger. And then we have minus 5.46, and x is bigger than that and smaller than minus 2. And then we have x is bigger than minus 2 but smaller than 1.46. And then we have x is bigger than 1.46. Sorry, this is supposed to be So now, let's sub in a value from each of these intervals to see if it's increasing or decreasing. So, from this interval, we're going to use 6, minus 6. So we have minus 6 equals, sub in minus 6 to the x value. Minus 6 to the power of 2 gives us 36, plus minus 24 minus 8 gives us 4. And then minus 6 plus 2 is minus 4 to the power of 2 is 16 plus times 2 is 32. And this simplifies into 0.125. This is a positive number, which means this interval is increasing. And now let's sub in value from this interval. Let's use minus 4. So we have minus 4 to the power of 4 times minus 4 times 4 minus 8. This equals to minus 8. And then we have minus 4 plus 2, which is minus 2 to the power of 2 is 4 times 2 is 8. This simplifies into minus 1. And this is a negative number, therefore this interval is decreasing. And then now let's plug in a value from this interval. Let's use 0. So 0 to the power of 2 is 0, and 4 times 0 is 0, and minus 8 gives us minus 8. And then 2 to the power of 2 times 2 is 8. This simplifies into minus 1. And this one is also a decreasing interval. Now let's plug in a value from this interval. Let's use 2. So 2 to the power of 2 is 4, plus 4 times 2 is 8, minus 8 gives us 4. 2 plus 2 is 4. 4 to the power of 2 is 16, times 2 is 32. This is a positive number, therefore this interval is increasing. So now, when there's an extreme point and the interval before it is increasing and decreasing, that gives us a max. And this is an asymptote. And when it's decreasing and increasing, it gives us a minimum. So that means we have a maximum at minus 5.46 and a minimum at 1.46. So let's find the coordinates of these points. So to find that, we just have to find the y value because we have the x values. We plug in the x values to f of x and find the y values. So 0.5 times minus 5.46 to the power of 2 plus 2, 0.5 to the power of 0.5 times minus 5.46 plus 1 simplifies into minus 5.46. And then 0.5 to the power of 1.46 times itself plus 2 over 0.5 times 1.46 plus 1 simplifies into 1.46. Now, the local maximum for 6 and minus 5.46, and the local minimum is 1.46. The reason why these are local, is because the maximum point is in a lower place than the minimum point, and the minimum point is in a higher place than the maximum point. That just proves that these are local and not absolute. Now, increasing, decreasing intervals. So, as you can see here, this is increasing, and this is decreasing, decreasing, and increasing. So therefore, this means f of x is increasing over negative infinity and 5.46, and it is increasing over 1.46 to positive infinity, and it's decreasing over minus 5.46, negative 2, minus 2, 1.46. Sorry, this one's supposed to be smaller than x. I just need to correct that. Let's move on to finding the inflection points. So to do that, first we find the second derivative and see where it equals 0, because an inflection point has the most or least rate of change, which means it is a minimum or a maximum on the first derivative, and the rate of change of that will be 0, as the rate of change of a minimum or a maximum point is 0. So we use the quotient rule to find f double derivative x. So now we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Let's find the derivative of the numerator and the denominator. So the denominator, when we simplify x plus 2, it gives us x squared plus 4x plus 4. So that times 2 gives us 2x squared plus 8x plus 8. And the derivative of that gives us 2x squared is 4x when you derive it, and 8x gives us 8, and plus 8, this is a constant, therefore it's 0. And then the numerators derived. X squared derived gives us 2x, 4x derived gives us 4, and minus 8 is 0. So now let's plug that in to our equation. So I plugged it in, and then I factorized, took the common factor out. So 2 times x plus 2 squared times 2 times x plus 2 gives us 4 times x plus 2 to the power of 3. And then that minus, we have x squared plus 4x minus 8 to the power times 4 times x plus 2. So let's write that here. And the denominator, let's multiply this by this. So let's simplify this. And then now we have 4 on each of these, so we're going to take that out. And then we have x plus 2 to the power of 3, and then x plus 2, and x plus 2 to the power of 4. Let's cancel these out too. So we're left with 2 here and 3 here. And then that leaves us x plus 2 to the power of 2 minus, x squared plus 4x minus 8. And you have x plus 2 to the power of 3. Now let's expand this one. So we have x squared plus 4x plus 4 minus x squared minus 4x plus 8 all over x plus 2 to the power of 3. We have positive x squared and negative x squared, and these two cancels out. We have positive 4x and negative 4x cancels out, and then we have 4 plus 8 on the numerator. And then this leaves us 12 on the denominator. This here is f double derivative of x. Now, to find the point of inflection, as I said earlier, we have to equal f double derivative of x to 0. So, multiply both sides by x plus 2 to the power of 3, and this leaves us 0 equals 12, which isn't true, and there isn't any x value that would make this equation true. Therefore, we have no inflection points. Now, let's move on to finding concavity. So, when the y value of the second derivative is over 0, which means over the x axis, over an interval, when the y value of the second derivative is bigger than 0 over an interval, fx concaves up, and vice versa for concave down. So when the y value of the second derivative is smaller than 0 over an interval, f of x concaves down. As we mentioned earlier, the vertical asymptote lies on x equals minus 2. So let's make an interval table accordingly. So our first interval is x is bigger than minus 2. And the second interval is x is smaller than. So our first interval is x is smaller than negative 2. And the second interval is x is bigger than negative 2. So let's plug in a value from each of these intervals to find if they're negative or positive. So from the first interval, let's plug in negative 3. So negative 3 plus 2 to the power of 3 equals 12 over negative 3 plus 2 is negative 1 to the power of 3 is negative 1. This leaves us negative 12. So it's a negative number, therefore this is negative. And from this interval, let's plug in a value bigger than minus 2. Let's plug in 0. So 12 over 0 plus 2 to the power of 3. 2 to the power of 3 gives us 8. 12 over 8. 12 over 8 gives us 1.5, which is a positive number. Therefore, this interval is positive. So since this is negative and this is positive, this concaves down and this concaves up. Therefore, the function of f of x concaves down over minus 8 and 2. Therefore, f of x concaves up over negative infinity and negative 2, and concaves up over negative 2 to positive infinity.